Howdy everyone, welcome back. We're going to continue with our little thing talking about some basics about capacitors, but today we're going to focus specifically on using energy in capacitors. And well, they store charges, they put them together in ways that feel uncomfortable to them. So it's got to store energy. That's what we're going to talk about today. Okay, what do we need to know? Well, we're really only going to add one equation on today. Last time we learned that the charge of capacitor is equal to its capacitance times the voltage difference over it. So now we have the potential energy is equal to 1/2 Q change in V. And so we'll notice that we have two equations, and that's going to allow us to rewrite this second equation in a couple different ways. So for instance, we could put this charge in, substitute it out, we'll get V squared, we'll get the C here, or we can take out voltage instead and get this equation. So the point is that, again, if we just know two of them, just like last time, if we just know two of charge or capacitance or voltage, we really know the whole thing. We have the whole picture, and the same thing for potential energy. Okay, we have a problem here, and we're going to be finding a few things kind of similar to last time, but with a few twists. So first thing we want to do, we have two capacitors. We know what their capacitance. We want to find the equivalent capacitance. We break these down to one capacitor. What's its equivalent capacitance? The one capacitor that if I switch them out wouldn't change anything. Well, these two things are in series. I can use the rule for series to find the equivalent capacitance, or the 1/over rule, and I can find the potential energy of that too if I wanted to. So I have this equivalent capacitance. I can find the potential energy of this equivalent capacitance. I don't know maybe the charge, but I do know the capacitance and the voltage. They tell me this is 12 volts. I've now found the equivalent capacitance, use the version equation of the two things I do know, put that in, we get 8.64 times 10 to the negative 4 joules. The next question, we want to find the energy in each of these capacitors. So we look at them, they're in series, so we know that each of them have to have the same charge as the equivalent capacitor, the one with just the one capacitor in it. Well, we can find out what that charge had to be. We go Q equals VC, put that in, we know that's equal, get the number, there it is, bam. And now we can use the version of potential energy, the things we know now. We don't know what the voltages of each of those capacitors are. We know what the charges are. We know the charge and we know the capacitance. We can use that version of the potential energy equation easily to get what we want. You note in the case, and actually if we were really paying attention and staring at this, we'll notice that if we added both of these potential energies of these two capacitors in series, that they would equal the energy for this equivalent capacitor. And this is generally true, so if I add up all these together, so I'm essentially adding up 1/2 QV of all these ones. So we know a bunch of things in series. When I added all the voltages, it should be the overall batteries ones. So we'll find, well, that's what we need to use to get the overall potential energy of the one equivalent capacitor. So it turns out that's kind of a neat little thing that's true. So we'll do one more thing. We'll change it up a little bit. We'll ask if now this circuit was in parallel, so instead the capacitors look like this, they're in parallel to each other, which voltage gives the same energy as an A? So we can go and solve this. First off, we can find the equivalent capacitance of two things in parallel. We just add them together. So we state that this new potential energy is going to be the same. We can go and solve for this change in voltage. Go back and solve for it. Find that it had to have been 5.7 volts. So I want to make a quick note here. First, we found out that if they are in series, one would store more energy than two, because one has a smaller capacitance than two. And you can see we get this inverse relationship. But here, it wouldn't be inverse, it would actually be linear. So actually it would be the opposite. Two would store more charge in this case. Sort of a weird thing to keep track of, but there you go. Here we have a little more of an involved problem. We have a battery. We'll be attaching it, disconnecting it, changing the distances between the plates. So first off, I have this capacitor here, has a capacitance of 3 microfarads, has some distance in between them. And we're told if the voltage is 6 volts, what is the potential energy of this capacitor? Well, okay, that's straightforward to do. We have the capacitance, we have the voltage. We can go straightforward, solve for the potential energy. Then we're asked, if the battery was disconnected and we actually changed the distance, we actually doubled the distance, we moved farther apart, then what happens to the potential energy? So if the battery gets disconnected, the charges are actually kind of stuck there. You can imagine instead of there being a battery here that's holding it together, it's just this broken wire. And so these charges, can have nowhere really to go. They're just gonna sort of sit there and stay there. So since the charge is the same, we're gonna get this relationship between C and V here using the Q equals VC stuff. We can find how the capacitance changes by just looking at what happens when we double the distance. So when we double the distance, we're going to get half the capacitance as we did before, where these primes are what's going to happen after we disconnect the battery. So capacitance is half it was before. It was 3 microfarads, now it's 1/2. So we have that now. We can go put that into potential energy. We have an idea about what the new capacitance and the new voltage are going to be. We can put that into our equation. So again, recall that we can get the new voltage by solving for it. We have this equation. We can move the new C over to the other side. We get this. So in here, we know that this relationship is 2. We just solve for that. And this, we get that 2 getting squared. We get a 4 out here. We get a 1/2 by exchanging the C prime for a C. And we'll notice that we'll get a 1/2 here. We'll get a 4 here. So overall, we'll get something that looks like 2 times the original PE against the original potential energy was 1/2 C V squared. So overall factor of 2, the potential energy now has doubled compared to the before. Okay, so now imagine we were attached it to the battery. So now the voltage is now what it originally was. So what happens now to potential energy? So the capacitance is still halved because we've increased the distance, but now the voltage is the same. What happens? Well, the only thing that changes here is this C prime, double prime. We just get the 1/2 C. Voltage doesn't get doubled. So overall, we get 1/2 the potential energy. Okay, thanks for joining me. A little quicker, a little more focused content, but let me know how it went. Thank you. Okay, bye.